Well, thank you everyone for coming. Apologies for the delay, we had a small technical hiccup. Let me crack on because I have a lot to cover. This presentation is based on a team effort, so that's myself and Dr. Tilman Wade from City University London. My name is Nikolay, I'm a data scientist at the Big Data Technical Team at IBM, and Dr. Wade is a senior lecturer in Big Data at City University London. And essentially he came up with the idea to look into parallelization of restricted Boltzmann machines for big data. So the restricted Boltzmann machine is a neural network. So the formal definition of a neural network, which probably most of you know, is that it's a massively parallel distributed processor that's capable of learning from experience. And the interesting thing is that the neural network stores the acquired knowledge in its synaptic weights, the connections between the processing units. This model is essentially inspired by the human brain, and it also exhibits certain properties that are similar to the human brain. So neural networks are capable of solving complex nonlinear problems. They're also massively parallel. They contain hundreds and thousands of processing units, and they're also fault tolerant, which is a very interesting property because if you think about it, if you write a program in, let's say, Java or Python or whatever, and then just remove like 100 lines from the source code at random, your program will quite likely, it won't function. It probably won't even compile. But with a neural network, what happens is the network exhibits what we call a graceful degradation. It will still work. It won't be as accurate as it used to be, but it will work. And that's kind of similar to the human brain, because if a person gets a stroke, they might lose the control of a limb or get a speech impairment or something, but hopefully they won't stop functioning completely. So that's the neural networks. And we have applications for neural networks in machine learning. We use them for function approximation, for classification, clustering, and so on and so on. But the topology and the design of all neural networks, because they vary, is kind of similar. You have those simple computing elements that we call neurons, and they are connected to each other. And a single neuron is again inspired by the brain cell neuron, and what it does essentially is you have connections to the neuron, and the neuron acts as a linear combiner. It sums up the signals that are coming over the connections, and then it passes them through an activation function. There are different types of activation functions. Some of them are linear, some are non-linear, some are stochastic in nature, and so on. And based on the type of the activation function and the topology of the network, you get different types of neural networks. You get things like multi-layer perceptrons, which are feed-forward networks. You have self-organizing maps, Hopfield networks. You have support vector networks, and so on and so on. But this lecture focuses on the Boltzmann machine and the restricted Boltzmann machine. Now, that's a Boltzmann machine. The Boltzmann machine is a fully connected, undirected graph. This one here on the right-hand side contains 6 neurons, 6 computing elements that are all connected to each other. And in this type of a neural network, we define something called energy function. This energy function measures the global energy of the system, and that's the state of each pair of neurons multiplied by the synaptic weight, the strength of the connection between the neurons, and any biases as well that are associated with the network. Now, if you have the energy function, you can also compute something that we call the energy gap. And that's the difference in energy based on if a certain neuron is on or off. And using these two metrics, you can compute also the probability of transitioning of the network to a lower energy state based on the probability of a single neuron transitioning to a lower energy state based on the energy gap. You see delta E here is the energy gap, and T is an artificial notion of temperature. That's a concept we borrow from metallurgy, where you want to model a metal, something out of metal, you heat it up, you bring it to a very high energy state where you can easily model it, and then you let it gradually cool down into a more stable energy state. Now, we run the Boltzmann machine by sequentially updating the units until we reach thermal equilibrium. So we let the network run until it reaches thermal equilibrium, which means that the probability distribution, the probability of global states has converged. Now, how do we train a Boltzmann machine? The probability of the network settling in any state is expressed by this function. This function here, you see KB is the Boltzmann constant, hence Boltzmann machine. T is the temperature, and Z is called a partition function, which is essentially the sum of all states of the network, all possible states of the network. And this function is, this partition function is very difficult to compute, because if you think about it, you have to sum up all possible states, and if the network grows, if you have many neurons, this is very computationally intensive. And you will recognize this formula is basically a canonical Gibbs distribution, by the way. Now, training the network means that we want to adjust the synaptic weights between the neurons in a way that they make the machine match the training data in terms of a probability distribution. And we do the training in two phases. First, we start by logically separating the neurons by saying, well, these neurons are the inputs of the network, these neurons are hidden variables that will model the distribution. And you do it in two phases. You start in the so-called positive phase, where you present inputs. Here you have 4 input neurons, V1, 2, 3, 4. You present some data. You clamp the inputs. You don't allow them to change. And you run the network until it reaches thermal equilibrium. At the end of the phase, you see each pair of neurons that is simultaneously on. You kind of detect them, and then you increase the synaptic weight between them. And then what you do is unclamp everything, let the network run freely. That's the so-called negative phase. And at the end, you kind of try to find what 2 neurons are simultaneously on, and you decrease the synaptic weight. This is essentially the so-called Hebbian learning, where you kind of enforce positive associations, you strengthen positive associations, and then you try to unlearn poor associations in the negative phase. But the bottom line is updating the weights is done based on the probabilities of 2 units being on during the positive or negative phase. And the bottom line here is that learning this network, training it, it's difficult, because you have to compute this partition function, and you also have to run the machine until equilibrium during the 2 phases. And this takes time. Now, there are some optimizations done in this model, like the restricted Boltzmann machine, where essentially we split the visible and hidden units into separate layers, and we remove the lateral connections between them. And what happened is that this restriction that we apply to the topology implies that the visible units and the hidden units are independent of each other, and vice versa. And this lets us to train the machine more effectively using similar update rule. We get the expected value from the training data, which we can do in a single parallel step, and then we sample the equilibrium distribution to get the expected value of the model, and we find the difference. Now, sampling the model is a bit more involved, but we can use tricks like contrastive divergence learning, where we can use a finite set of steps to get the direction of the gradient. So that's done. OK. That's the theory. I'm happy that you're still here. That's as difficult as it gets. Now let's talk about the applications. Now, we can use RBMs in a wide range of applications, like dimensionality reduction, collaborative filtering. We use them for classification, and so on and so on. And I want to give you an example. Now, let's say that I want to do image recognition. I want to do handwritten digits recognition. I have, let's say, hundreds of images with handwritten digits, and these images are 28 by 28 pixels. So I have 784 pixels in total. Let's say that I want to put a logistic regression classifier next to the data and train it to recognize the digits. Now, my logistic regression classifier needs to have 784 input features, right? 1 for each pixel. And I have to train the classifier, it's a multinomial regression to recognize based on what pixels are on or off, what kind of a digit is presented in the data. And that's difficult, because 784 input parameters is maybe OK, but when you're dealing with big data, you probably work with images that are like 1 million by 1 million pixels, maybe satellite images or geospatial data, and so on and so on. And then The bigger the data is, the more input features you need, and then your classifier will struggle. So what we can do is instead we can plug a Boltzmann machine in the pipeline. And here we have 784 neurons in the visible layers, but just a handful of hidden variables, just a handful of hidden layers in the hidden layer, like 50. And we can run the machine and train the machine to recognize features from the images. And let's say once the machine has converged and it's fully learned, it will start picking up features like these. And then we train the logistic regression classifier based on the features alone. So when this logistic regression classifier sees feature, let's say 1, 2, and 4, it will say, well, that's something like a 2, so probably the digit 2. If it sees features like number 3 and 5, it will say, well, this looks like an 8. But the idea here is that now your classifier has only 50 inputs. It doesn't have to deal with hundreds and hundreds of inputs. So that's one very good application for restricted Boltzmann machines, that's feature extraction. Now, that's nice, but RBMs for big data are still very difficult because A, they're computationally intensive. B, big data means we have to train machines with millions and billions of neurons. And that's problematic. If you try to estimate the parameters, the synaptic weights, for a machine with billions of parameters, this can take weeks. And people have been looking into optimizing the learning process by parallelizing it. And most of the efforts went into GPU-based parallelization. And there is this very interesting article by the team, and you probably recognize Andrew Ng from his Coursera machine learning course. He's one of the authors of this paper, and his team essentially used GPU-based parallelization to reduce the training time from weeks to 1 day. However, in this paper, in this article, they still recognize some constraints. For example, they say that 99.5% of the time of the training actually went into moving the data. Because the GPUs can only operate on the shared memory that's in the GPU, you have to copy all the training data from conventional memory into the GPU. And that takes a lot of time, a lot of time. The second problem is that you're constrained by the amount of memory you have in the GPU. So if you have 4 gigabytes of shared memory in the GPU, that's all the data you can fit in. And this is peanuts, thinking about big data. So the logical question for us was, can we do this in Hadoop? Can we, instead of using, dedicated GPUs and trying to parallelize there and abide to those constraints, just use a bunch of inexpensive nodes and do it there? Is it possible? Well, of course it's possible, but we started looking at what kind of existing frameworks have implementations of restricted Boltzmann machines that are native to Hadoop, and we couldn't find any, so we decided to write one. But the problem we quickly realized when developing custom machine learning algorithms for Hadoop is that we have to handle something called optimal execution plans. And I want to show you what the problem is. If you want to implement a custom machine learning algorithm in Hadoop, like something extremely simple like linear regression, the way you do it, one way of doing it, using normal equations, is to get your data in matrices, X and Y, input features, target attributes, then set up your hypothesis, which is a straight line or a hyperplane that fits the data, and then establish a cost function like the quadratic distance between predictions and actual values, and try to minimize it. And in this case, because the quadratic function is a convex, you can just take the derivative of the cost function with respect to the model parameters, equate this to 0 and solve. And then you get something like this. So you can get the parameters using x transpose x, the inverse of x transpose x times x transpose y. And if I have to write this in R or Python or something like this, that deals with small data, let's say R, I will do this. I will establish a system of equations. Left-hand side is x transpose x, right-hand side is x transpose y, and then I can use the solve function in R to solve my system and provide the coefficients. The problem is this doesn't scale properly. So here is an example. Say that I have this cluster configuration in the bottom right corner where I have 7 gigabytes of memory in my driver and I have 3.5 gigabytes of memory for my workers. That's Hadoop, right? And I have this data set where I have the X matrix on the top right corner with 500 features and 300 million observations. And then I have my Y vector with 300 million observations. That's about 4 terabytes of data. Now, if I want to implement this in an optimal way for my cluster, what I will do is not just go ahead and implement it as in R, but what I will do is I will take the transpose of the vector Y, I'll pin this in the distributed cache, then I'll split my X matrix into 1K by 1K blocks, and I'll piggyback 2 operations in a single map task. That's X transpose X and X transpose and Y transpose X. And after the computation, after the reduce phase, I will end up with A and B transpose. But the total amount of data of A and B is less than 2 megabytes at this phase. So what I can do is from there, I can just finish the computation in the driver. I don't need map reduce operations. So what I can do is on the driver, just get B from B transpose and go solve. And that's the most optimal way of solving this problem for this cluster and this data set. The problem is what happens when you change the cluster configuration or when you change the data set. Well, if I add additional features to my X matrix, if I, say, move from 500 to 1,500 features, then a single row of the matrix no longer fits one of my 1K by 1K blocks. So what I have to do is I have to break my computation into a series of map steps for computing X transpose X. So I have to rewrite my algorithm. If I increase just the number of observations, just the number of training examples, what happens is Y transpose grows so much that it doesn't fit the distributed cache anymore. So again, I have to chain a series of map steps for computing X transpose Y. And the bottom line here is that if I change my dataset or if I change my Hadoop cluster and the memory available, my optimal plan is no longer optimal, and it's quite likely it won't work at all. So we were kind of thinking, how can we solve this for the RBM use case? And luckily, it appears that there is a way. That's Apache SystemML, which is a declarative machine learning platform for Apache Hadoop. And what SystemML does, it's an open source project, you can go and look it up on GitHub, is essentially it has an interface. It provides 2 high-level languages called DML and PyDML, which are based on R and Python. They kind of mimic the same syntax. So if you're comfortable with R or Python, you're comfortable with DML and PyDML. And what SystemML does is you can write your custom machine learning algorithm in DML, and then you pass it to SystemML for execution. SystemML will look at your algorithm, but also look at the input data. It will look at the dimensionality of the input data, and it will also look at the cluster configuration. It will look at the number of nodes and the amount of memory that's available. And then it generates a set of execution plans. And it uses a cost-based optimizer to find what plan is the most optimal one for this algorithm, this data set, and this execution backend. It also does other clever things like low-level operations optimization, like piggybacking multiple operations in the same map steps and so on, and it does rewrites. So if you do something like distributed matrix multiplication, where the number of non-zero elements in one matrix is 0, it will say, yeah, you don't really want to trigger a distributed matrix multiplication for this case, because we know the answer, and it's a matrix of zeros. Now, the backends, you have an option. You can run SystemML on a single machine, so you can prototype your algorithms and test them. Option B, you can use Hadoop as a backend, and you can use MapReduce, or you can use Spark. And option C is SystemML supports OpenMPI, so you can use OpenMPI to offload the execution to a supercomputer. And in all 3 cases, you don't change anything in your algorithms. And that was wonderful. The problem with SystemML was that there was no restricted Boltzmann machine implementation in SystemML. So we had to write one. And how difficult can it be? Turns out it wasn't that difficult. It took me like a few days. That's just an example of the source code. We had a bunch of scripts, some of them training the network, others running observations through the network and so on. But you can see the positive phase and the negative phase. That's the DML language, so it looks kind of like R, and how we sample the equilibrium distribution. Okay, then we decided to do some functional testing. After we had the RBM running on top of SystemML, we staged up a Hadoop cluster on Amazon, just 6 nodes, 2 management nodes, 4 data nodes. We were kind of constrained in terms of budget. We put SystemML on one of the management nodes, and we decided to first see if the network performs at all and if we are getting meaningful results. So what we did is we used the MNIST dataset, which is a dataset of handwritten digits, like 60,000 training examples and 10,000 test examples. Apologies for the typo on the slide. So what we did is essentially we reproduced this use case. We started feeding images to the restricted Boltzmann machine, and we had actually 200 neurons in the output layer. And we ran the machine until convergence. So now if you think about it, we kind of had the machine trained, and it had learned certain features, and we were interested in seeing what did the machine learn. So if you think about it, each neuron in the hidden layer is essentially connected to 784 neurons in the input layer, and that's a 28 by 28 pixels image. So we decided to plot them, to plot the knowledge that was accumulated by the machine as features. And that's what we saw. That's just the first, I think, 36 features or so. And you can see that the machine had learned some abstract representations. Some of them look like ones, some of them look like kind of twos and threes and fives and zeros and so on and so on. And what happens is when you pass a training example through the trained machine, some of the neurons in the hidden layer will fire. If you pass the number 4, all neurons that kind of resemble 4 will likely fire. So our machine was learning, and we were quite happy. The problem is how this will impact accuracy. So we started testing pipelines using the machine with support vector machines, with naive-based classifiers, with decision trees, and so on and so on. We didn't see any significant impact on the accuracy. So using the features instead of the raw data wasn't hurting accuracy at all. On the other hand, we saw a massive improvement on the convergence time. So that's one example. We trained a multinomial logistic regression classifier. And the training using the raw dataset took 230 minutes. The training using the learned features took a minute and 20 seconds. Actually, when I ran this, I went to grab a cup of coffee, and when I came back to my machine, I saw the Linux prompt, and I was like, oh, damn, shoot, it probably failed. And then I realized, because I knew how long I had to wait for the first run. But yeah, it had converged. So that's like 150 times speed up. Now, we had a functioning machine. The question was, will it scale? So we took another data set from Project Gutenberg, which contains like text files, ebooks essentially, with some metadata. We transformed the data set into a set of labels and feature vectors. We used the subjects for the books as labels, and then we used bag of words to transform the text into feature vectors using frequency of occurrence. And then we sampled the data set, and we established small data sets of 10,000 books, 20,000 books, 40,000 books, and so on and so on. And we wanted to run this in Hadoop. And we started with the MapReduce backend. And this is what happened. 10,000 books we were able to process. The next milestone, 20,000 books, we waited for 7.5 hours and we gave up. And actually, when we looked at the execution plans for the 10,000 books, SystemML was cheating, because it was looking at the data set and it was saying, well, this data set is so small that I can run everything in the driver, so I don't need MapReduce at all. So it was just like a local execution, right? And we said, well, yeah, we don't like this. So we started looking at the algorithm, and because we were using mini batches in the training process, we said, maybe the problem is that we use mini batches, and in the sense of Hadoop and MapReduce, those mini batches generate hundreds of MapReduce jobs. Maybe we should ditch the mini batches, try to do the entire training in one go. And this helped a bit. We were able to process 20,000 books, but then on the next stepping stone, 40,000, the cluster, kind of gave up with an out-of-memory error. That's expected because we were trying to add to load and process too much stuff in memory. And this was a bit discouraging. And then we switched to Spark. And that's what we got. Actually, we managed to process 20, 40, 60, 80, and we stopped at 100,000. Probably we could have gone farther, but we had to submit the presentation for the conference. That's fresh data, so we're still working on it. So we were able to scale up to 100,000.